right? So one of those are series of common misconception, right? Uh, Current drop in saturation. Okay, so let me explain what this. This is a very common error that students carry away after discussions related to a bipolar junction transistor. And let's see what this misconception is. We've all seen this plot, right? Collector current versus the collector emitter voltage. These are the output characteristics. And this characteristics is drawn at different values of the base current that you see here, right? So here I have a base current of 100 microamperes here. So what does it mean? That for this graph, base current is constant, right? So for this graph, base current is constant. And what we are doing is we're changing the collector emitter voltage. So we are starting from, say, higher collector emitter voltage here, and we're reducing the collector emitter voltage here. And the current starts dropping, right? The current starts dropping here. And eventually the current, if you go to low enough collector emitter voltage, the current even becomes zero. If we go beyond it, the current may become negative also, right? So the issue is, why is this? So first of all, what is happening as I decrease the collector emitter voltage here? As I go from right to left, what is happening? Collector emitter voltage. See, the base current is kept constant. So collector emitter, as I reduce it, the base collector junction is getting forward bias. We know the transistor is entering into saturation region. So it's entry. All this region is saturation region here. And so the current is dropping. After a while, reasonably constant, but after a while, as you go, as the collector base junction gets more forward bias, the current starts to drop and then eventually falls to zero here. Now the issue is, why does this current drop? As I go here, so we know that the base collector junction is getting forward bias. Why does the current drop? Okay. Well, let's see a possible explanation here. So this is our emitter, this is base, and this is our collector. Okay. And we know that in the forward active mode, what is happening? The emitter is injecting electrons into the base, and this junction is reverse bias. And the electrons, we know, if we assume it to be uniformly doped base, the electrons diffuse, and the profile of the electron, excess electron density is like this, right? So this is how it goes. And we know that, so this is in forward active mode. The transistor has not gone into saturation. Collector base junction is reverse biased here. We know that this kind of a electron density profile gives us a electron current, which is Q times area of the junction, diffusion constant, del N zero is at this point here. Excess electron density is negligible here. We take it as 0 divided by WB. So that gives us the electron current. And what is my collector current equal to? At this point, collector current is primarily equal to the electron current, because at this junction, this is reverse bias. Which other component is there? The reverse leakage current. And reverse leakage current we assumed, is usually very small as compared to this component. So IC is basically equal to IN, right? So this is we have seen earlier. Now we are saying we are forward biasing the junction. So in forward biasing the junction, what happens is this junction gets forward biased. What is the effect of the forward biasing? This junction starts injecting, this will no longer be 0. So what we get is, the picture that we have is, base emitter junction is forward biased, so I have certain electron density here. Collector base junction gets forward biased here. I expect a certain electron density here. What would be the current now? IN will be equal to the slope of this particular line here. So it will be equal to QADN, say, delta N0 minus delta NWB divided by WB here, right? So this is the current here. So as we are forward biasing the collector base junction, what is happening? What is happening as we are forward biasing the collector base junction? Is this term increasing? This term is increasing. Then what is happening to the slope? Slope is decreasing, right? So this IN term that you see here is decreasing. And in a forward biased collector base junction, there is a injection of holes also here, right? So what is the net collector current now? Collector current you see is IN minus the injected hole current here. So why is the collector current reducing? What would you say? What is the reason for reduction in collector current? IN is reducing, and in addition there is a hole also current here, which is also subtracting from it, right? So why is it really reducing? Is it this factor? Or is it decreasing because of IPC here? Or is it decreasing because IN is reduced? What is the reason? What is the dominant factor? Why would you say IN? Because you expect this whole current to be small, right? Okay, so which is obvious, because let's look at this picture, same picture here. So IC is IN minus IPC. Now note that suppose I start from here. If you look at this particular one here, how much is the current? 30 milliamperes. And let's say I go to a point where the current has fallen somewhere here, 15 milliamperes. Right? So current has fallen from 30 to 15 milliamperes. Now, how large can IPC be? This whole current. How large can it be? Who supplies this whole current here? Base. How large can it be? The base current is only 100 microamperes, which is 0.1 milliampere here. So when this current has fallen from 30 milliamperes to 15 milliamperes here, it can't be this factor. This factor is very small, 0.1. So what is the dominant cause for falling in IC? IN itself is falling, right? IN itself is falling. So it's obvious that delta IC, when I see from here, when I see current falling, change in delta IC is basically change in delta I. And why is IN falling? Why is IN falling? Is this a reason that I have first in forward active like this? Then as I decrease the collector emitter voltage, my base collector junction gets forward biased, it becomes like this, and therefore the slope is changing, right? And my this thing here. This is where the misconception is. So you're all agreeing to it. So let me state it. We are all saying that collector current decreases in saturation with decrease in collector emitter voltage because of increased electron injection from the collector into the base, right? Correct? This is all we agreed to, right? That this slope is decreasing. We all agreed to it, right? So you all nodded your head. You said, yes, this is the reason. And I'm saying this is a misconception. This is a misconception that the collector current is reducing because of increased electron injection from the collector into the base here. Let me show you why it's a misconception, why it's not correct. Okay. All right. Let's come back to this picture. Right. So for the sake of discussion, what we'll say is we start from 30 milliamperes here, and we are going to come to a place where it will drop to 15 milliamperes. Right. Now, look at this term here. This is, if you look at this picture here, electron density profile here, this is in what? Forward active mode. In forward active mode, what is the collector current at this particular point? 30 milliamperes here. Base current, 0.1 milliamperes. Now, we said, well, once I come to 15 milliamperes, what is the picture that we have? Conventional picture, if you would like, is this green one. That's the picture that we have, right? And we said now, for this green one, we said, the net current would be 15. Base current is still 0.1. Agreed? This is what we said. The collector current has fallen from 30 to 15. This red line gives us the picture at 30 milliamperes here. And the green line gives us the picture at 15 milliamperes here, where the current has fallen to half. Right? So IC2 is 15 milliamperes and IB is 0.1 milliamperes. Why is this picture wrong? Well, let's take a bipolar transistor. Let's take a bipolar transistor. Typical bipolar transistors, I'll show you some results later on, has a forward current gain which is high and reverse current gain which is low. Okay, as an example, I'm taking a forward current gain of 300 and reverse current gain of 10. Okay, I'll show you a real transistor with current gains which are of this kind here. 300 and reverse current gain of 10. So now let's see why this picture is incorrect here. Let's look at this green line here. This is a picture we are saying exists at what? 15 milliamperes here, when the transistor is in saturation, right? This green profile that you see here. So I've drawn here. This profile, what did we say, can be broken into two parts here. One is due to the electrons which are injected from the emitter. The other one is electrons which are injected from the collector. So this current that you see here, here can be written as what? As a current which is a difference of two currents, IF minus IR. IF is like what? this current here, which is only due to electron density injected from the emitter. IR is what? Is due to electron density injected from the collector here. If I take the difference of the two, it's nothing but the green line that you see there. So IC2 we are saying is IF minus IR. Right? Now, what is IF? What is the picture that we have built? This is in the forward active mode. And this is now in saturation. So IF for us, what we are saying is the following, according to this picture. We are saying collector current has become 15 milliamperes. IF remains same as 30 milliamperes here. Because of increased electron injection from the collector, this IR is 15 milliamperes. And 30 minus 15 is equal to 15 milliamperes. This is what we have said. If you look at this is the electron density profile in the forward active mode. And we have said in saturation, when the current has fallen to 15, the electron density profile has become like this here. Has become like this. Right? What is this current? This slope, what does it correspond to? 30 milliamperes here. That's the same slope here. 30 milliamperes here. And this must be equal to 15 here. So we said 30 minus 15 will give rise to a net current of 15 milliamperes. So now, if the collector base junction is injecting 15 milliamperes of current here, sort of 50 milliamperes here, right? What does beta R mean? Beta R means that the ratio of the whole current here and IR should be how much? 10. So how much whole current do we want injected into the collector then? IPC should be 15 milliamperes divided by 10 equal to 1.5 milliamperes here. Where will this 1.5 milliamperes come from? How much current do I have? Base current is fixed at 0.1 milliampere here. Where will it come from? Are you seeing that this picture is inconsistent? This cannot be. If you build this picture here and say current has decreased because of this decrease in slope, then what you are saying is this decrease in slope implies that I have a reasonable electron current here, higher electron current here, which is almost 15. And this 15 would imply a current injected from the base into the collector here, a whole current of the order of 1.5. I don't have 1.5. I have only 0.1. So this picture cannot be right. This picture that first I have this and then I have this cannot be right. This picture is wrong. I cannot have current decreasing because of this particular picture here. But we agree with that. But we agree that. So what we are saying is, if you assume that this picture is right, then your net current is 30. This is 30. IF is 30 minus IR equal to 50. How large can IR be? How large can IR be? This current. If you want to calculate the maximum possible current IR, what does it depend on? The ratio of IR and IPC is what? Reverse beta. How large can IPC be? 0.1. Right? Because the base current is constant at 0.1. So how large can IR be? 1. So how large can this be? 30 minus 1? 29. You can't go to 50. It's just not possible. This picture is not right. The current is not decreasing because of change in slope like this here. So how is current decreasing then? How is current decreasing? Well, let me show you how current is decreasing here. This is the picture at 30 milliamperes here, right? Forward active mode. Correct? This picture, the red one. Now current is decreasing. Why? Because of, look at this picture here, the green one. Look at the green one. The current is decreasing not because of you have a lot of injection of electrons from the collector into the base. Why? Because the injection of electrons from emitter to the base has decreased. See, the picture that we were carrying is, we have a bipolar transistor. As we are forcing the bipolar transistor more and more into saturation, the base collector junction is getting forward biased. More and more electrons are getting injected into the base here, and the slope is decreasing. That may be happening, but that's a small phenomenon. What is happening is the electrons that are injected from emitter to the base is actually falling also. And look at the picture here. The electrons that are injected from the emitter to the base has fallen from this here. This is in forward active mode when the current is 30 milliamperes here, and this is in the saturation mode when the current has fallen to 15. This current this electron density has fallen. There is an increase in electron injection from the base here. You can see here it's no longer zero. If you look at the green line, it's no longer zero here. But it's not that significant, this particular part here. What is more significant phenomenon? That the electron density here has fallen to so much. Not that the electron density here has increased from 0 to something. It has, but this is the significant phenomenon. So let me show you what is happening here. I can calculate, maybe I'll give you an example. I'll ask you to work this out. So what is happening is when you're going from 30 to 15, at 15, what has happened at 15 milliamperes here? What has happened is the forward current here, because the electron density is decreased, is about 15.48. It has fallen from where? From 30 to 15.48. What about the reverse current? The reverse injection was 0. It has increased only to a small amount, 0.48. And then there is IPC here, which is even smaller here. And you can see the net current is close to 15. So why has the current fallen then? All right. So why has it fallen now? Yeah, interesting, right? Why has this current fallen here? So what is happening is, right? So what you are seeing? So this is the conventional picture, right? Conventional picture was saying, well, you have injected so many electrons into the base and the slope has become smaller. Well, you have injected electrons into the base, but not that much. That's not so significant. What has happened is you have injected less electrons into the base here from the emitter side, and the current has fallen here. So you're right. Why is this happening here? Well, look at this base current. This is the picture here. Base current here. When you are in forward active, what is happening to the base current? It goes into the emitter. And this current is reverse bias negligible, right? So what do I have? If I have 0.1 milliampere here, how much is this current? 0.1. And how much is this? 0. Now when I forward bias, what happens? This junction is getting forward bias, so there's a base current is needed here also. So as an example, what is happening is this is fixed 0.1. This has become 0.048. And this has become 0.052. A current division has occurred. Now, if less current is here, what will happen now? Less current means what? Less forward bias. Less forward bias means less injection. So, because the collector is taking away the base current. Base current is fixed. And collector is taking away the current from this junction into this junction. So, less current is available here. And less current is available means less injection also. Less forward bias and less injection here. Right? So this is the reason why what is happening is that it is dropping. The electrons which are injected into the base have dropped here. And therefore the slope has changed and the current has dropped. So what is happening is, as you are decreasing the collector emitter voltage, what is happening? Yes, VBC is increasing. Collector base junction is getting forward bias. But what we have forgotten is that as collector base junction is getting forward bias, what is not talked about is that base emitter junction forward bias is decreasing. The forward bias on the base emitter junction is actually decreasing. And we can see why, right? More current is diverted here, less is available here, which means less forward bias. And base emitter voltage is actually falling. And as base emitter voltage is falling, less current is injected into the base here and the current falls. This is the dominant reason, not that more electrons are injected here. All right. So what was the misconception? Misconception was here that the collector current is dropping from 30 from here in forward active mode to saturation here. Why? Because of increased electron injection into the collector here, and we said the slope is becoming smaller here. What is the real thing here? Collector current decreases in saturation with decrease in collector emitter voltage primarily because of decreased electron injection from the emitter into the base. This is the correct picture here. The electron injection has fallen, and that's where this thing here. So decrease in VCE results not only in increase in VBC, but is also accompanied with decrease in VBE. So if you actually go and measure, let's say, what is happening as I go from here and down here, you will find that the base emitter voltage is actually decreasing. Okay, so let me show you now some experimental results here. This is a transistor BC, common transistor BC547, NPN transistor here. So we got the TAs for the course to measure this particular transistor. This is the typical characteristics that we are talking about. Output characteristics, IC versus VCE, right? And we have biased it at 3.17 microamperes fixed current, and it gives us a collector current of 1 milliampere here. Okay, and then as you're reducing the collector emitter voltage, you can see here as stage comes, the collector current starts falling and eventually goes to zero here. Okay, right? So this is what we were discussing. Beta for this transistor, forward beta is 315, close to 300 that we had taken, right? Now note, we were saying, let's say I start from a point here where collector current is 1 milliampere, and then I go to a place where the collector current has fallen to half, let's say 0.5 milliampere, right? So 0.5 milliamperes, where do I get? At VC equal to 0.12. Somewhere here, VC equal to 0.12 is there. Okay. This is the reverse beta. In the reverse active mode, beta R, you can see here beta R is a, this increasing function and is a little bit complicated behavior. But if I'm around 0.5 to 0.6 volt here, my beta R is less than 10. Right? So what I'm trying to tell you is beta F was how much? 300. Beta R is what? If I'm here, is about 10, less than 10. Right? Okay. So, yeah. Now, as I'm going from here, collector emitter voltage, as I'm decreasing, the collector current is falling. What is happening to base collector voltage? Increasing, right? Base collector junction is getting more and more forward bias, which is fine. You can see here. Base collector junction is getting more and more forward bias as you're reducing the VCE. Now, what was our explanation? We said as you make the base collector junction more and more forward bias, the base current gets diverted to base collector junction and less current is available for base emitter junction. So what should happen to base emitter voltage? It should drop, right? So let me now plot base emitter voltage. Can you see what is happening? Base emitter voltage here is constant, but as the collector current starts to drop, what is happening to base emitter voltage? Can you see here? Dropping. Base emitter voltage is dropping. So as the current is dropping, the base emitter voltage is dropping. What does it imply? Less electron injection into the base. Okay, so let me blow it up and show it to you how it decreases it. So here, when the collector current is constant, the base emitter voltage is about 635 millivolt. So at 1 milliampere. When the current drops to 0.5 milliamperes, close to point, which was happening at 0.12. At 0.12 volt. What is the base emitter voltage? 618 millivolt. From 635 to 618 millivolt. It has dropped. 618 is at 0.12. If I go 0.12, somewhere here 618 is there. Right? Base emitter. How much is the change in base emitter voltage? 17 millivolt. It has dropped by 17 millivolt. Now, what has happened when you have gone from 635 to 618? Collector current has fallen from 1 milliamperes to 0.52 milliamperes here. Now, if the change in base emitter voltage is 17 millivolt, how much is the change in electron injection into the base? How do you calculate? E to the power VB by VT. So how much is it? So if I look at exponent Q delta VB by KT, how much is it? 0.5. So how much is the electron injection into the base? It's reduced by a factor of 0.5, factor of half. That's why the collector current has fallen to half. Not because of increased electron injection into from the collector into the base. It's happened because of decreased electron injection from the emitter into the base here. Right? So that's the correct picture. But why has this misconception formed? Why do students carry away this misconception of this is happening here? What is the reason? So the misconception actually comes from many times in the books. What happens is people discuss this situation here. That I have, if you look at this transistor, I have base emitter voltage which I've applied is fixed. And now what I'm doing is I am taking my transistor more and more into saturation region. And how do I take my transistor into saturation region? I take it by making the junction more forward biased. So in forward active mode, we know if I have 0.7, let's say, and -1, well, this is the picture here. Now, if I keep base emitter voltage fixed, right, and I change my base collector voltage, now why will the current reduce? This end is fixed now, right? The moment I keep base emitter voltage fixed, this end is fixed. And when I change this, now it will become, say I make it 0.682, then it becomes like this here. And the slope has become half. Right? So this picture is fine if I keep my base emitter voltage constant. But bipolar transistors are not voltage driven devices. You don't keep base emitter voltage constant. What you do is, as you saw in the output characteristics, we keep the base current constant. And then this picture is not right. This is not what is happening. So if you discuss this, if you discuss this case here, and you don't discuss the previous case where base current is constant, what happens is we keep on carrying this particular picture in the mind that as I'm collector current is reducing. Why? Because of this happening. More electron injection from the collector into the base. So this picture forms into our mind because we discuss this and we don't discuss that particular case, and we keep on carrying this particular picture. And when we show it to the students, why has it decreased? This is what it will tell you. It has decreased because of this here. Because of more electron injection, because this is what they are remembering. This is what they're remembering, that this is at fixed one. But this is not what is happening in the output characteristics. Base emitter voltage is not fixed, but is actually dropping. So it's a different situation. Okay, that's where the misconception forms here.